All right, from yesterday, okay. The main focus was what? Because I don't know. I was here. I was taking notes as well. But the main structure behind yesterday was what? Okay. Now, these different types of cells, as you had noticed, we all need to have a place to start to gain experience. So that's why Mr. Wagner had was in charge of yesterday. I thought maybe that would be a good spot to jump in. And with that, I said, hand that vocabulary sheet out afterwards, and then we'll be able to make sense of that today or also moving forward. So with that, can you name a type of cell that was discussed yesterday? A Schwann cell? There's one that's really hard to say, starts with an O. Oligodendrocytes. Okay. There's microglial cells. And then astrocytes. So then you're also given an acronym, which I think was it CAM-PSS? CAM-PSS. Okay. So when you look at the functions of those assorted cells, what might be one of those that has the closest in functions, I should say? Schwann's is one. Okay, now, they have similar functions, but they're found in separate parts of the body. What would we mean by that? Yeah, you're exactly right, but which one's which? The Schwann cells are found in the peripheral nervous system, and then what you see is the oligodendrocytes would be in the central nervous system. I don't know if it found layers. Okay, so the brain and spinal cord, so you would presume that that's where it's found, and I believe it would say that on your vocabulary sheet then as well. So then I believe you also went through different types of neurons that are found within the nervous system, and even as some of you wrote down what we're going to discuss today, that type of neurons is not only just the most common, but the one we spend all of our time on, because it is the most common, because it's found within the brain. So is that a unipolar, a bipolar, or a multipolar neuron? You had a 33% chance. Okay, and to answer that, what we mean by a multipolar then is that we could even say if this is our central neuron right here, is it only sending signals out and not receiving any? They receive and send. So here, this can send a signal going in this direction. Okay, you can also receive information here. This one, okay, is this going to be a portion that receives information or sends it? Why is that right? Right, so how can you, because you're naming the correct structures, but how would you know that, though, by looking at it? Well, that's true, too, but that doesn't answer by looking at it, though. It's something really simple, and you say, I knew that. No, you're getting closer. Whether it's an oligodendrocyte or a Schwann cell, what is the advantage of these getting thick or more thicker? We said yesterday, for instance, this electrical cord, or even our speakers here. Sometimes the information gets through there, sometimes it doesn't. Okay? because I might have to wiggle the wire on that speaker, or the, I don't know, the adapter that goes into there. Is that what you would call this? Whatever this, what would we call this, just so we're on the same page? Speaker adapter? Because that's what it goes into, okay? That's what we'll call it. So if that sometimes sends information, sometimes does not, we called that a short, okay? So what happens is, the example we gave, why is it that someone of my advanced age might be standing here and doing this? Or it could be ALS, okay? So what that means is this is still functioning, okay? But that doesn't answer why it's doing this, okay? But what happens is in the axons that we see, that when we're sending, gosh, I must have spilt a little bit on my thumb and fingers, moving a little too quickly. So we know this is an axon because it is more thick, and then this is a dendrite because, what did you say, it's got one line to it? Are you looking close enough? Oh, here I thought it was something important. Oh, okay. But what happens in some of these disorders, okay, this myelin sheath, typically when we get a little further on in a diagram, this is that myelin on there. And what happens is if that's one side, what might happen is there might be gaps in there because that myelin sheath is starting to break down. So sometimes the signal gets through, sometimes it doesn't. And that's what creates that jitteriness. Just like on that speaker adapter, the signal gets through, but sometimes you got to wiggle the wire a little bit, then it goes through. So that's what happens with some of these disorders in the nervous system, is that it basically shorts out. So that's how you tell the difference between an axon and a dendrite, as these are much, much thicker than what the dendrite is, because that's receiving the information, and then, of course, the axon is sending that. Now, this doesn't mean anything to you right now, but we will get to that in just a moment. Okay, so moving forward then, we're done with the cells of the nervous system, and we move on to, we're actually a little bit ahead of schedule, which is just fine. So then, but for me, I just know that these are found in the central nervous system. I don't remember CAMO or PSS. It doesn't mean that that's bad to do that. That's just not how I learned it. But it certainly makes sense when, again, when you say CAMO, we know it's the central nervous system. The A is what, the astrocyte? Okay. And then the M means microglial, correct? And then the O would be this. And then the PSS would be your Schwann cell and what was the S? Satellite cell. And that's in which portion of the nervous system? Yeah, peripheral one. Okay? So then, moving forward then, we're talking about nerve impulses. Okay? Those are also known, we could refer to them as action potentials. Okay? A voltage potential is something you might use a voltmeter to measure how much current is moving through a specific type of wire. Yes? Oh. You only have... Well, dang it. So I think that's where we would say, my mistake, your fault. Let me just do this really quickly. So rather than, we will just read through this, and then we'll talk about tomorrow, and then we'll finish up seeing how Robert is developing. Okay. because once we read through this, we can make sense of this. Okay. So when something becomes polarized, that means you're just having a difference of current going through. Then that's how the nervous system works. Okay. So in this case, this bioelectric current flows through your nervous system. So we know that the human body can conduct electricity for two reasons. One, that's how our nervous system works. Also, we're mainly composed of what substance? I think I heard it, but mainly composed of water, which is a polar compound, which means you have a difference in net charge from one side of the compound to the other. Now, with this young gentleman yesterday morning, he said, I tried to wash all this substance off, but it just did not work. Because if you get an oil-based substance, was it oil paint? Okay. So if you get that on your skin, soap and water, no matter how much you put on there, it's just not going to come off, because the polarity of the water will not take off the nonpolar substance of the paint. You have to use something that is similar in nature. So if the paint is nonpolar, you have to use a nonpolar substance to get that off. Diesel, gasoline. Said he used was it paint thinner or mineral spirits, okay, which is also nonpolar. But you really don't want to be using a lot of that on your skin if you don't have to, because your skin can absorb some of those alkane materials. So we used acetone, because what happens if you get fingernail polish on clothing? Does it come out fairly easily? No, because that's a nonpolar substance. So if you want to get the nonpolar, let's say, fingernail polish off your nails, you don't scrub them with soap and water. You need to break that down chemically. In order to do that, you use fingernail polish remover, which of course is what compound? Acetone, mainly. And that's what he used yesterday. He said it worked pretty well. Okay, so what we see here, this bioelectric current, is something that you actually learned last year and 2 years ago in biology. So how do materials get into and out of cells? There's 4 processes. What's one? Starts with a D. And it's not darn. I swear he said, oh darn. Diffusion's one. It's another type of diffusion, but it starts with an F first. Facilitated diffusion. And then what about water? That's osmosis. Okay? And then finally, the last one that takes energy is called what type of transport, maybe? Because the first 3 are passive transports, because it doesn't take any energy. The 4th one that does take energy is not passive, but rather active transport. Active transport, yeah, now I remember. Okay. So with that, we'll discuss this tomorrow. Okay? And then we'll certainly see evidence of this today in that video. But what I want to show you is what we see here. Okay? So inside this cell body, when we're talking about action potentials, notice it said, has anyone been to an athletic event where they've done the wave? I was watching Miami and Denver, I think. And you saw the crowd, they were doing the wave. So how does that happen when you do the wave? One person starts that and they do this, right? Then what happens? Then the next person. Then the next person. So it starts here and it's just a wave that keeps going around in a circle. Okay? So these action potentials are very much like that doing the wave at some of these athletic venues. I just use that as an example. So what we see happening here, okay, in order to maintain a type of current that's going through there, you can't send two in, two out, two in, two out. That does not maintain a voltage. You have to send 3 in and 2 out. So this is our sodium and what? Sodium potassium pump, and that's where this comes from. So what happens is, okay, in a type of passive manner, can sodium diffuse into the cell membrane pretty easily? If it's high on the outside and low on the inside, can it diffuse pretty easily? Yes. Yes, it can. And for the same reason, potassium on the outside, can that diffuse into here pretty easily? No, because there's actually more on the inside than there is on the outside. So then these will diffuse through 2 at a time. In this case, 1, 2, 3. Where we get the active portion of this is, even with these 3 sodiums going in, would it be hard for that to go against a concentration gradient? Yes. So that's where the energy comes from active transport. So once these 3 sodiums are now inside, so they're gone, the concentration gradient is still higher on the outside. So these sodium ions are now in, so they have to be pumped back out again. And here it's being pumped against its concentration gradient. The main thing that we want you to know about this, okay? Two at a time. I don't think you say it like that. 2 at a time. Okay? Sodium, however, three in and pumped back out again. This is the key right here because, again, it's pumped against its concentration gradient. And that's why we refer to the sodium-potassium pump as a type of active transport. So, and I think it went quite smooth, yet, well, I don't know, from what I could tell, when we say quite smooth, there really wasn't any, let's say, disruptions in the class, and from our end, we really appreciate that. Everyone was paying attention like we want you to do, because we are in here because we probably will be using this content in the future. Then the last thing we want you to know, why didn't we start on this side? Why did we start over here? Yeah, because the impulse is going in this direction. So when we see this concentration changing inside of here, it starts in this direction. This unequal rate at 3 to 2 is going to move away from the cell body, and that's exactly how that happens. It's going in that direction, which it has to because this is the axon and that's the dendrite. Okay. Again, we will discuss that a little further in depth tomorrow. Now, that's with the idea that I'm going to remember to print that off for you. So we will see how Robert is doing in the development of his brain. And the main type of neurons that we see are what type? We see in a little bit of some unipolar neurons, but they're mainly multipolar. Okay. Now, one of the things that we see, I gotta stand here so the microphone can pick that up. If there is a nerve conduction going in this direction, and then there's another one coming from the other direction, the video had illustrated them two impulses collide. So what that means is Robert is going to look in one direction or another, not because of reflexes, but why? Because he wants to, okay? Which we said just for the opposite reason, and because since we explained this in this class, this direction, or in this manner, for those of you walking down the hallway, I always observe, yep, we look down the coach's hallway, yep, we look down towards the lobby, but that's just by habit. Okay? There again, I think you probably look, even if there's nothing happening, you look that direction because you want to. Of course, you can also do just the opposite and not look in that direction because you don't want to. Okay? So, continuing with Robert.
Trying to coordinate what he sees with controlling his hand is an extremely difficult task. But Robert's cortex has been preparing for this challenge. It has vastly overgrown the number of connections it actually needs, allowing him to test billions of alternative pathways for every action he takes. Now, a process of elimination begins. Whenever Robert gets close, the best connections carry the strongest signals and survive.
So, what can you presume from this? What is it that is growing in diameter? Okay? It's being coded by what? Starts with an M. It's being coded with myelin. Okay? And it's natural. Your brain goes through this pruning process. Okay? You have the most number of central nervous system cells. When you're born, it goes through not a complete transformation, but about 2 weeks after you're born, there's an explosion of nerve cells. Then eventually, they're looking for the best conduction, and when that happens, that myelin really grows on there, and that's why it's the best conduction.
Signals begin to wither and die. Robert's cortex is pruning itself into the most efficient structure. It takes time, and it can be frustrating. But Robert is building a powerful tool, which will last for the rest of his life.
There we are, Bobby. We're going for a walk. Yes, we are. Yes, we are. Aren't we?
Only 4 weeks later, and Robert is close to getting what he wants. The redundant connections in his cortex have been pruned away. Now the final touches are being added. Specialized cells called glial cells are busy coating the strongest connections with a layer of fat. These fatty sheaths insulate the signals, improving their efficiency. When Robert reaches out, strong signals fire along the optimum pathways. Directing his hand precisely where he wants it to go. This tiny grasp is an enormous leap forward.
Here, monkey, that's mine. Come on.
Robert has started to take control of his domain.
All right.
Robert has only just begun a journey of learning that will last his entire life. The process of rewiring in his cortex will slow down, but even when he's 90, it will still be forging new connections and being shaped by the world around him. We learn to control our muscles and master movement, but there are times.
Okay. So, again, this is where we'll stop for today. And we'll pick up with this action potentials tomorrow. Okay. So catch up to you next time.